I know it seems like we just started chapter 24, but we're going to finish it today. Chapter 24 is just the difference between two means and its confidence intervals and its hypothesis test, and that's it. We've already talked about confidence intervals a lot before. Hypothesis tests a lot before. At this point, again, we should be getting the hang of it, okay? So, when you're doing a hypothesis test, so I'm going to add in a screen here. You're doing a hypothesis test. Alright, so when you're doing a hypothesis test, what are the steps? Well, you write hypotheses, right? A null and an alternative. Okay, excellent. Then you check conditions. The conditions are still the same as they were for confidence intervals. Randomness, 10%, independent groups, and nearly normal. Check both sets of data. Okay? Then you name the test in a sentence, right? Then you do the mechanics. And there's three pieces, pretty much. One, the standard deviation or standard error, depending on what you're talking about. Two, the test statistic, which is Z or T, which is found by doing the statistic minus the parameter divided by the standard deviation of the statistic. And then you find the p-value using a calculator or a table, normal CDF, TCDF, those types of things. Okay? And then after that, you make a conclusion. Then you're in your conclusion. You say if the p-value is high or low, depending on alpha. You reject or fail to reject the null hypothesis, and you keep that all in context, right? We have done this a lot, right? It's not as confusing as it first was. Okay, so today, difference between two means, we call that a two-sample t-test. I know that is shocking to you that we would call it that. They haven't all been named, so they're ridiculous and easy, just like this every single time. All right, so the first one is hypotheses. And so just like when we did proportions, our null hypothesis is that the difference is equal to, here it says delta naught, but what do we normally assume the difference is? We generally assume there's no difference and make that 0. So you have mu1 minus mu2 equals 0. Again, don't use x bar or y bar for mean because we don't use sample statistics in our hypotheses. And so then your alternative will just be that mu1 minus mu2 is greater than, less than, or not equal to, somewhere in there. Okay? Then we check our conditions, right? Name the test, got it? We go back here after the test, we do the mechanics. So the standard error formula right here, it's on the AP formula sheet. The test statistic is right. The difference in means minus the parameter, the difference given in the null hypothesis, generally 0, divided by the standard error. And then from there, you find the p-value. You find the probability that t is greater than or less than something. And you have to list the degrees of freedom since you're using a t. But again, can we find the degrees of freedom by hand? No, not so easy. It's not like n minus 1 when it was for one sample mean. We have 2, so we have to use the calculator. It's working out well for you guys in this chapter. Okay? So then if you get a p-value, make a conclusion. I think we get the gist, right? So let's do a problem. We can see if we have any questions from there. Quick note about pooling. When we did a 2 proportion z interval, we pooled because we had the square root of pq over n plus pq over n, okay? So we knew the standard deviation, and we were assuming that the 2 proportions were equal to each other, and so to assume that they were equal to each other, we could only have 1p. That'd be the same. So we pooled to put it all together, okay? Well, in this case, we don't technically know the standard deviation. We know the standard error we're estimating, okay? And you can pool. It would be a pooled t-test. We could do it. But by doing that, we have to assume that the variances are equal, and that's another condition. And it gets kind of tricky because how are you going to really know if they have equal variances? There are a couple of advantages, a few more degrees of freedom, and a much simpler degrees of freedom formula. But you have to pool the variances and think about another assumption. And it's often not true that the variances are equal, and it's difficult to check. So the book says, so I'm backing them up, we recommend that you use a 2 sample t-test instead. In general, in essence, what I'm trying to say here, it's never wrong not to pool. So just don't do it. If you can't be wrong by not doing it, then just don't do it. You still have to pool for 2 proportion z intervals. You do not have to pool for 2 sample, or sorry, not for intervals, for 2 proportion z tests, but you do have to pool, you do not have to pool for 2 sample z tests, all right? So you don't have to do it. So we won't. Now, first question. We're not actually going to do a test. It's going to ask you a question. A company institutes an exercise break for its workers to see if this will improve job satisfaction, as measured by a questionnaire that assesses worker satisfaction. Scores for 10 randomly selected workers before and after implementation of the exercise program are shown. The company wants to assess the effectiveness of the exercise program. Explain why you can't use the methods discussed in the chapter to do that. Don't worry, we'll give you another chance to do this the right way. So, if it's asking you this question about explain why you can't use the methods, you should immediately be thinking of, oh, I should check the conditions. If the conditions are met, you can't do the test. So looking at this, what condition isn't met? The same thing you missed in our last test when we talked about chapter 22 stuff. You have 10 workers, and they're the same workers, and you're getting 2 responses. So this is not independent groups. You have one group of people with 2 sets of responses. Okay? If you're worker number 1, and you talk to worker number 2, maybe you influence each other, it gets kind of tricky. So this is not independent groups. And so we're going to do this in chapter 25. If you're kind of keeping track of things, we did 1 proportion z intervals and tests, the 2 proportion z intervals and tests, and then we're going to do 1 sample mean intervals and tests and 2 sample intervals and tests. So you would think that this unit should be coming to a close, but there's this extra chapter. This extra chapter is all about what happens when you don't have independent groups and you actually have paired data. So chapter 25 is going to be all about what happens when you have paired data. Okay, that gets a little bit more tricky. So another chapter to go about means. Sorry. Okay? All right, 1 question, and they'll be done. Researchers investigated how the size of a bowl affects how much ice cream people tend to scoop when serving themselves. At an ice cream social, people were randomly given either a 17-ounce or a 34-ounce bowl, both large enough that they would not be filled to capacity. They were then invited to scoop as much ice cream as they liked. Did the bowl size change the selected portion size? And here are the summaries. Test an appropriate hypothesis and state your conclusions. Assume any assumptions and conditions that you cannot test are sufficiently satisfied to proceed. So we're going to write ourselves some hypotheses. So do you want to do large minus small, small minus large? It doesn't really matter. You guys are probably going to do large minus small because large is large. Large is larger than small. Shocking. So mu L minus mu S is equal to 0. Now, the alternative is kind of tricky here. You have to pay attention to the question that they're asking. Did the bowl size change the selected portion size? So it's not saying, did the larger bowl equate to more ice cream? They're actually asking if the bowl size influenced portion size. So we're going to say that the difference is not equal to 0. Okay? All right, we're going to check our conditions. But again, I'm not going to take the time to write them all out. We have done this enough. So, is it random? People were randomly given. So there's a randomness in this experiment. We are giving people random bowls. I guess it's not an experiment. It's an observational study. We're not actually giving any treatments. No, we are. So 10%. Again, see, it's weird. You have let's see here, how many people? 26 people for the small bowl. It's 26 less than 10% of all people that could have received a small bowl for ice cream. That sounds weird, so you don't have to check it. Do you have independent groups? Yes, you have 26 people and 22 people that were randomly assigned to these different bowls. And then we have nearly normal. Now, our sample sizes are 26 and 22. So do not say the sample sizes are large enough, because technically they're not. We also don't have a picture, which would be awesome. So assume any assumptions and conditions that you cannot test are sufficiently satisfied to proceed. So we're just going to go with it. It's nearly normal. Move on. Okay? We name the test. We're going to complete a 2-sample t-test. Perfect. First thing I'm going to do is find the standard error. We've got 2.91 squared over 22. That's s squared over n for the large bowl. Plus we have 1.84 squared over 26 for the small bowl. Our t is statistic. Statistic minus the parameter. So our statistic is the difference in the two from the sample, 6.58 minus 5.07 minus the difference from our null hypothesis, which is 0, divided by the standard error. Now, when you calculate all that, you get 2.103. For the p-value, we're still going to write this all out. Again, we're still going to do it in the calculator. I need to find the probability that t is, well, it just says not equal to. So we have to decide what tail to do. Well, since it says not equal to, we multiply this by 2, and we just use the tail that we've got. So we've got a positive number, so t is greater than 2.103. If it was negative, we would have less than. We just use the tail and multiply by 2. So again, here's our problem. We don't know the degrees of freedom. I can't use TCDF. I can't use inverse T. We have to use the calculator. So I'm going to bring my calculator out here. Stat test. We're doing a 2-sample t-test. Again, 2 options, data and statistics. All right? If you have data, you would have 2 lists of numbers. Statistics, we have means and standard deviations, what we have. So we did large minus small. So we need to do all the things with large first. So our mean is 6.58. Our standard deviation is 2.91. And a sample size of 22. For the second small bowl set, we have a mean of 5.07 ounces. Standard deviation of 1.84 ounces. And a sample size of 26. Now I have to choose which hypothesis we're using. We're doing not equal to. By us telling it's not equal to, it's going to multiply by 2 for us for the p-value. Pool? No, because we're not going to pool, right? Ever. Calculate. And it tells us T is 2.103, had that, and our p-value is 0.04 3, and it said our degrees of freedom was approximately 34.3. You need to make sure you mention those things. Okay? Now, we're going to make a conclusion. The p-value is less than an level of 0.05, right? So if it's less than, we reject the null hypothesis. And then to put that into context, we were just saying if the difference was equal to 0, and it's not. So it seems bowl size affects portion size. Okay, so in this experiment, you're given different bowls, so it's 2 different treatments. We measured, figured it all out. These bowl size affects portion size. We'd have to do more testing to be more specific if we were looking for large, bigger than small, that kind of thing. Okay, that's it. That's how you do a test. I'm going to give you what to do for homework tonight. And then we'll kind of wrap things up the next day, trying to make sure everything in chapter 24 is taken care of. Okay?